Hey guys, in this video I'll be going over the solutions to problems D and E, cutting words and sorting queries from AtCoder Beginner Contest 217. So starting with problem D, we basically have a long piece of timber of length L, and so these circles are basically points on the timber. Let this be point 1, 2, 3, 4, 5, 6, 7, all the way up to L. So for this, let L be 7, and they are connected to each other. So what the problem is asking you to do is, you have two types of queries. For the query of the first type, it'll give you some point on this timber, and you have to cut it from there. So for example, if the query gives you 0.4, then you have to remove this connection over here. So you remove that. And the second type of query basically asks you for the length of the piece of timber which contains some given point. For example, after this query, I can ask you for the length of the timber containing 0.6. Now, because we cut it at this point, the length will be 3. And for the timber containing any of these points, the length will be 4. So we can go on and keep on cutting the timber at points. And it's also given that if we cut the timber at some point, then we won't get a query asking for the length of timber at that point, or get a query asking us to cut it again at that point. Yeah, and one important constraint here is that L can be up to 10 to the 9. So we know that we can't store an array of size 10 to 9. That's just too much memory usage, and we won't be able to iterate over it anyway. So what we want to do is we want to maintain a set of integers. So essentially for the query of the first type, oh yeah, so let me just call this set st and let it initially have 0 and L as elements, right? Now for the query of the first type, whenever we make some cut, let's say we made a cut at 0.4, then what we'll do is we'll just insert that point into our set. So now if we want to query some point, for example 0.3, we can find out what the length of the timber is by just finding out where the cuts are using our set. So we'll find the cut made the next cut to the right of 0.3, which will be at 0.4. So we'll search for this. You can search for an element in a set in log of n time, where n is the size of the set. We'll search for this, and we know that the cut to the left of 0.3 will just be the element to the left of this 4. So that's why I added 0 and L, because if there is no cut to the point of length to the left of 0.3, then that'll just be 0.0, which doesn't exist. And it'll just make it easier and prevent casework in case we have an empty query or stuff like that. So let's say we queried 0.3, we found this 4. So we add 4 minus 3 to our answer, because we can see that the length over here is 1. And to the left of it, we have a cut at 4, which is basically not a cut. But yeah, so then we can add 3 minus 0 to the answer, because we can see that we have another timber of length 3 over here. So which is plus 3 minus 0, which gives us 4. And yeah, we can see that the length of this whole piece of timber is 4. So that's basically how you solve this problem. It's a direct data structure based problem. And the code for it is pretty simple. We take in our input, for the query of type 1, we basically add that cut into our set. We use the upper bound function to find the cut made after this. And since we're given that no cut was made at this point, upper bound or lower bound, either of those functions would work. This gives us the next cut in log of n time. So we add that cut minus this point to our answer. Then we find the cut made to the left of it. We add that to our answer and we just print it. And yeah, this is a pretty straightforward problem. And the total time complexity would be Q of log n, yeah. O of Q log n, sorry, yeah. It'll be O of Q log n because for each query we do basically O of log n operations. So yeah, that's it for problem 4. Let's move on to problem 5, which is E. And in this problem, we have 3 types of queries. So initially we have an empty array A, which is empty, an array A which is empty, and then we have Q queries, and queries can be of 3 types. So the first type of query asks us to append an element X to the end of array A. So if we have some array A, this is just a random array, and I have a query of type 1, it'll give us an element X and we have to add it to the back of A. Now for the query of type 2, we find the element at the beginning of A, we print it and then we remove it. So the first element here is 1, so we'll print 1 and then we'll delete it from this array. And the third type of query, which is basically the whole problem, is we have to sort the array A at some given time in ascending order. So for example, if our array looked like this, and we got a query of type 3, then we have to sort it in ascending order. So it'll become 1, 2, 4. And what makes this problem hard is we can have queries to add elements after this as well. Now, if you get another query to sort it, sorting an array, the fastest way to do that is in n log n, where n is the size of the array. And if we keep on doing this for each query, you can estimate that an upper bound on the complexity would probably be q into n log n, which is just way too slow. So how do we efficiently sort the array, or instead of directly sorting it, how do we actually simulate that process? And I have 2 solutions for this. One involves segment trees and the other one involves just multisets and small to large merging. Now the segment tree solution has a time complexity of q into log of n, and the one with small to large merging and multisets is O of q into log square of n, or q actually. Yeah, there's no n in this problem. Yeah, and it's actually better than O of q log q squared because it's kind of like you can consider it as constant factor, or every time we have set merge queries, because of when they occur, we actually won't have exactly q elements. So an upper bound, you can just consider it to be O of q log q squared. So yeah, I'll go over both solutions, starting with the one involving segment trees. So the segment tree one, we want to make a segment tree of pairs, which is basically stores the element and its index. And initially, let's just initialize our segment tree with this value. Infinity is just some very large value, and let's just say its index is 0 to avoid indexing issues later on. Now, every time we want to add an element to our array, what we'll do is we'll just take the index of that query. For example, if we wanted to add element 4 and the index of that query was 10, we'll just set index 10 of the segment tree to a pair of 4 and its index 10. So our segment tree will basically look like this. I mean, this is a random drawing, but you can see that we'll have holes in the middle, which are basically this pair of garbage values, if you want to call it. And yeah, and then we'll have actual elements as well. So how does this help us? We saw that sorting the array at each step was too slow, but we just need to print out the starting element of each of the array for each query. So we really just need the minimum element, because when you sort an array, the smallest element comes at the start, and after printing it, you remove it. So then we go towards the second smallest element. So yeah, we initially just want to we want to store the location of the sorted array basically. So if we know that the first 4 elements are sorted, then I'll restrict my segment tree queries to the first 4 elements. And if I need to print an element, I'll query the minimum value, which will be 1. I'll move it. I'll set that index in the segment tree to infinity. Then again, querying the minimum value will give me 2. I'll set it to infinity. And then I'll keep on doing that. And so there will come a time when all of them become infinity, and we need to just expand our write point so that we query a single element. So we just want to find the first index in the segment tree where the value is not infinity. And then if we want to sort it again, then I can just set the right query point of my segment tree to the index of that query, which tells us to sort it. So yeah, that allows us to simulate sorting the array, and we can solve this problem in O of q into log q. And let's also look at some code for that. So this is just my segment tree template. It's an iterative segment tree. You can use a recursive one. There's literally no difference, just constant factor speed up. And this is segment tree of pairs. This is the initializing value, and the merge function just returns the minimum of those 2 pairs. Now we take in our queries, and R is basically the point up to which we restrict our segment tree queries. For a query of type 1, we set that index to the pair of that value and that index. Now for the queries of type 2, like I showed you, our range can be full of infinities and have no real value. So we want to keep on incrementing our write pointer until we find some value. And so the total time taken by this would be just O of q into log q, because we have like at most q elements, so we can't make more than q queries for this statement. Yeah, so that's just O of q into log q. After that, we just query that value. So we restricted our range up to R. We query it, we print the minimum value, or actually it'll be the value at the starting of the array. And the reason why we stored that index was so that we could actually set it to infinity. So we'll do that. And of course, for queries of type 3, we want to sort the array. So we just set the query point of our segment tree, the right endpoint, to the index of that query. So we don't want to care about the infinities in the middle. So yeah, that's it for the segment tree solution, which is O of q into log q again. Right. And now for the second solution, which uses small to large merging and multisets, no other data structures. It is a bit slower, I think, but yeah, it's still pretty good. And small to large merging is a pretty useful technique. If you don't know what it is, then I'll probably leave a tutorial in the description below, a link to a tutorial. And yeah, if you just read up on it once and then come back to this, small to large merging isn't that hard to understand. It's basically if we have n sets initially with 1 element each, then every time we want to merge 2 sets, and yeah, every time we want to merge them, we only merge the smaller one into the larger one, because what that essentially does is it doubles the size of the smaller set. So every time we perform a merge, at least one set has its size doubled. There are n elements, so we can only, so for each element, it can only go into log of n sets because we always double its size, and we can't double its size if we don't have, so we can't go over n elements doubling its size. So the complexity for that just comes out to be n log n, and because inserting an element into a set takes log of n times each, and we, for each element we put it into log of n sets, that's just n log square n. So yeah, that's just small to large in merging in short, but I'll leave a link to a tutorial down in the description below. All right, so the observation here is that we have a sorted array, right? So for example, this could just be sorted. We would have gotten this array, and then we would have gotten a query to sort this. Okay, let's just assume that this is sorted for now. And now we can have queries to add elements, right? I can add 7, 5, or whatever. Now, if I get another query to sort this, I don't want to use the inbuilt sort function to merge these. That is too slow. But what I can do is I can pick up the smaller of these two sets, right? Either, so both of them have the same size. Let me just add a few elements here, right? And if I get a query to sort this, what I want to do is I want to pick up the smaller set and merge it into the larger one. Now, one thing to keep in mind here is that this part is not sorted, so we have to maintain two states for this, which is basically maintain an array storing this suffix in non-sorted order, and maintain a multiset storing this in sorted order, so that we can efficiently merge them together. So we want to merge this into this, and yeah, we can just iterate over every element and in this multiset and put that into this multiset. And now we can just swap those two multisets, saying that this multiset is now actually the whole sorted array. And we can keep on doing that. So by the logic for small to large merging, this should come out to be, well, better than this. Yeah, it should be better than that because of the reason I explained earlier. But yeah, that's essentially the solution. So, and now deleting elements is easy. We know that we, right, so there's one more thing to know. When, if our multiset is empty, then we just look at this array over here, the raw array we store in the order they're added. Because if it's empty, then we only, so this is equivalent to that moving the right pointer of that segment tree in the previous solution. So yeah, let me go over the code. It will become clearer after that. So right, taking the number of queries, sorted STs basically contain the prefix, which has already been sorted. And this is basically the current suffix, which isn't actually sorted, but we're maintaining this multiset so that we can efficiently merge these two sets. And this is just a deck and not a vector, so that I can delete elements from the front. Queries of type 1, we take the current multiset and the current deck and insert that element into it. Queries of type 2, if the sorted set is empty, then we want to use our deck and print the element from the front from that. Then we want to erase it from that deck, and we also want to erase it from the respective multiset. Otherwise, if the sorted set does have values, we just want to print the smallest one, which should be at the beginning of that multiset, and we can erase it. Now for the third type of query, where we want to sort the array, we can just clear out our deck. We don't need it anymore because we're going to merge the two multisets together anyway. This is just a neat way of swapping the two sets in case the size of one of them is larger than the other. So we just need to write code to iterate over elements of one set this way. So we go over the elements of the current set, multiset, and we just put them all into the sorted array set, and then we can just clear out this multiset. So yeah, that's it. I hope you learned something new today. I think this small to large merging solution was pretty neat. And yeah, don't forget to subscribe to the channel and share this video if you enjoyed it. Also, leave comments on what you would like to see next, and I'll see you in the next one.